In this part of the video, we will do chapter 16 in class exercise 3. We will solve a problem for the calculation of velocity using relative motion analysis. So let's read the problem statement. If roller A moves to the right with a constant velocity VA of 3 meters per second, determine the angular velocity of the link and the velocity of roller B at the instant theta is 30 degrees. So look at this link AB. You can consider that this is the wall and this is the floor, and this is a big rod which has one end resting on the floor and the other end is in contact with the wall. And then the end which is on the floor slides towards right with 3 meters per second. And when this angle is 30 degrees, this end B moves down and this entire rod AB also rotates counterclockwise. So we need to calculate the angular velocity of the link AB and the velocity of the roller B. I can also explain that with the help of this small prop which I have prepared. So this is the wall, this is the floor, and that's our link AB. Okay, so A is in contact with the ground and B is in contact with the wall, and then this link AB, when it slides, okay, link AB is under general plane motion because it's not pure rotation or it's not pure translation, but link this end A is in translation, but the entire link AB is in rotation. Okay, so this is the situation. So we will solve this problem using two different approaches. For the first approach, we will use the scalar solution. So we won't make use of this equation, but we'll just use the pure scalar solution. That means for all the velocity components, we will divide it into its horizontal and vertical parts, x and y parts. So no cross product, but just pure scalar solution. So let's draw a diagram, kinematic diagram for the scalar solution. So this end, so first define our coordinate system. So let's say that this is our coordinate system. This is x, and anything going right is positive, and this is y, and going up is positive. Now end A slides towards right, so this is the velocity of A. So this is positive 3 meters per second, which is given in the problem. B goes down, so it's actually negative. We don't know the magnitude of that velocity, so for now I'll just put magnitude VB. Now this is speed and the direction is given by the arrow from the graph. Now what about the velocity of B relative to A? So link this end B has counterclockwise rotation relative to A. So you can consider that this AB is a big like a disk where A is the center and B is the point on the disk. Then the velocity of B relative to A is tangent to this position vector and it points in the direction of rotation. So this is the velocity B relative to A. Now this angle, if this angle is 30 degrees, then the angle this V relative to A, VB slash A mixed with the horizontal line is 60 degrees. So next step is we write the equation for the sum of the velocity, horizontal components of the velocity, that is the velocity along x coordinate, and then we'll write the separate equation for only the y component of the velocity from all three velocities. So this is VA, by the way. Just one more thing I would like to add here is that VB relative to A, it has this direction, but the magnitude of this velocity is omega AB multiplied by R AB. Okay, so it's this omega AB, which is counterclockwise angular velocity of link AB, and RAB is nothing but the length of link AB, which is 1.5 meters given in the problem. Be careful, this is just the vector scalar solution, so RAB is not same as RB slash A. This is vector, this is scalar, this is just the length of the link. Well, this is length and direction. So scalar approach. So first step, resolving along x direction. So we write the equation for all the velocity components along horizontal direction only. So VA is positive, so that's positive. VB is vertical, so it does not contribute for x direction, but VB relative to A is pointing here, which is at an angle to x and y, so it has both horizontal and vertical components. The horizontal component of VBA is VBA cosine 60, and that will point towards negative x direction. And vertical component is VBA sine 60, and that will point towards negative y component. So for now, we will consider only horizontal component of VBA, which is minus VBA cosine 60 is equal to 0, because these are the only two velocity components present along x direction. And now we will substitute VBA in terms of omega and RAB. So it's now VA minus omega AB multiplied by RAB cosine 60 equal to 0. So we can also substitute the values of velocity that we know, that VA is plus 3. So it's 3 into omega AB. This is RAB is 1.5. It's given in the problem. Cosine 60 is equal to 0. When you solve this equation, you'll get value of angular velocity of AB, and that is 4 radians per second. And this is counterclockwise, and counterclockwise velocity is positive. We have discussed this a couple of times in previous lectures. So that's our one of the answers. Now the second answer is we need to calculate the velocity of B, okay, that is this velocity. So now we need to resolve the components vertically. So resolving along y direction. So there is one component from VB which is negative, so it's minus VB. Then vertical component of relative velocity of B with respect to A, which is minus VBA sine 60 is equal to 0. And now we need to substitute in this equation omega R. So it's minus VB minus omega AB multiplied by RAB sine 60 equal to 0. We know the value of omega AB, that is 4. We know the value of RAB, which is 1.5. Sine 60 is constant. So when you solve this equation, you will get value of VB. And if you round it to 3 significant figures, it will be 5.20. And unit is meters per second because it is linear velocity. And the negative number indicates that it's going down, because we have assumed that going up is positive. So which is right, which makes sense because VB is going down. So our final answers for VB is just 5.20. And to avoid any confusion, I always suggest that you write the positive number and you indicate the direction of velocity by arrow. So these are our two unknowns that we have determined using the scalar approach. Now in the next part of the video, like in the same part, we will solve the entire problem using vector solution, and we'll get the same answers. Okay, so now we will solve the same previous problem, this problem, using vector approach. So we will make use of cross product, and the velocity we will represent as vector, so with ij components rather than just using the magnitude as we have done here. So I'll quickly draw the problem. So this is the problem, which is, this is end A and this is end B. Okay, and A has velocity which is 3 meters per second towards right, and B has some downward velocity, but we don't know what is that value. Okay, and this link AB has counterclockwise rotation. But so we define our, so this is our kinematic diagram. Now the next step is the coordinate system. So this is x, this is our positive, this is y, that is positive, and this angle is 30 degrees. And this is velocity of b relative to a, because b relative to a has rotational motion. Okay? And we know that the length of the link is 1.5 meters, so I would say RAB is 1.5 meters. Now we need to apply cross product here, so let's revise the cross product rules that at some point we read in statics. So we have three vectors I, unit vectors I, j and k. Cross product of I with j, that is I cross j, gives us positive k. So this is the positive sign. So I cross j gives positive k because it's going positive, counterclockwise is positive. Similarly, j cross k gives us positive I, and k cross I gives us positive j. So just remember this simple counterclockwise circle of ijk. Now if the counterclockwise is positive, then clockwise is negative. So k cross j is negative I, j cross I is negative k, and I cross k is negative j. So we'll make use of this in our solution. So let's write down the vector equation for this problem. That velocity of b we are calculating relative to a, and a also has sliding motion towards right. So velocity of b is nothing but velocity of a, which is right, plus velocity of b relative to a. Now see, I am using the arrow, so it's a vector solution. VA, I'll further expand this part, velocity of b relative to a, which is rotational motion, pure rotation, which is omega AB cross R b relative to a. And this is our equation number 1. Next step is we will write each of this velocity vector using the unit vectors or Cartesian coordinate notation. However, we need this vector RB relative to A. So what is this RB relative to A? So this is position of a vector which goes from A to B. So basically it's this arrow which goes from A to B. This is RB relative to A. So I have drawn the arrow, like I hope you can see that in the video. And this length of this link is 1.5 meters. So let's first figure out this. So RB relative to A as a vector has two components. So it is this arrow. It's actually the tip of my pen is the tip of the arrow. Okay, so that's the arrow. And this angle is 30 degrees that you know here. Okay, so I hope you can read it now. So we need to find out I and j components of this vector. So I component or x component is 1.5 cosine 30 I, and it's going towards negative I, so we'll put negative sign. And then the y component is 1.5 sine 30, and it goes towards positive y, so we'll put positive j. So let's write down position vector. So it's 1.5 cosine 30 and I put negative sign here, and this negative because it's going left, plus 1.5 sine 30, and I'll put j here, that's for positive j motion. You can actually simplify, you can do this math here and simplify this this to constants. So 1.5 cosine 30 is 1.299 I, and 1.5 sine 30 is 0.75 j. Okay, so this is our position vector. Now what is velocity of A? Is vector notation, it's 3I, because it's going towards positive axis, so it's 3I. Velocity for B is its magnitude and its direction J, but it's negative J because it's going down. Okay, look at this. Omega, omega AB, we don't know its magnitude, so we can say its magnitude is omega AB, and its direction, this is counterclockwise. So to find the direction, we make use of right hand rule, and then thumb points towards the positive direction. So thumb is going up, that is positive Z, and when I bend my fingers towards counterclockwise direction, so this is K. Okay? Because unit vector for Z direction, positive Z direction, is positive K. So let's substitute 1, 2, 3, and 4 into equation 1. So substituting in equation 1, we'll get minus VBJ is equal to 3I plus omega AB K cross minus 1.29, 9 one more time, I plus 0.75 J. Next step is we need to finish this cross product here. So we need to multiply this constant 1.299 with omega and then do the K cross I and then plus sign, and we'll multiply omega AB with 0.75 and K cross J. So let's do this. So it's minus VBJ 3I plus, sorry, I should put the negative sign here. Because this is negative, so this negative will come out, so it's minus 1.299 omega AB. So just multiplication of these two constants, and then in the bracket it's K cross I, then this plus sign, and then 0.75 omega AB, and in the bracket it's K cross J. So I hope so far so good. Then next step is minus VBJ 3I minus 1.299 omega AB. Now it's K cross I. What is K cross I? Let's look at this. So K cross I, it's counterclockwise, gives us positive J. So we can replace K cross I with positive J in this equation. And what is K cross J? So if you look at the previous diagram here, so K cross J, so we are going in the opposite direction of the positive sign. So K cross J gives us negative I. Okay. So we have to put negative sign here, minus 0.75 omega AB, and this is K cross J is negative I. Okay, so that's negative I. Let's see. Next step, we have done this styles of problem in statics. So we need to separate now I and J components and basically convert this one vector equation into two scalar equations, one for I, one for J. So separating I and J parts. So when we do this, let's do this for I part. Now there is no I part on the left side of equality sign, so it's 0, then it's 3, and then this is not I part, but this is ith part, so it's minus 0.75 omega AB, and let's call this equation number 2. And then for J part, there is J part here, so it's minus VB equal to, there is no J here, but there is J here, so we just write the constant that's multiplied with J term, so it's minus 1.299 omega AB That's it. Okay, that's the third equation. Okay. So when you solve equation 2, you get the value of omega AB, and then you substitute that omega AB here and multiply that with minus 1.299, then you will get the value of VB. So, and when you do this, you will find the answers that omega AB is exactly 4 radians per second, and the direction is counterclockwise, and the other one, VB, is 5.20 meters per second, and it's going down. So these answers are exactly same answers that we have got with the scalar approach. So this is a very good example where we have compared both this vector and scalar approach side by side. So this is our scalar solution, that is vector solution. I suggest that you watch this video and try to do both the solutions on your own, and then you can always come back and look at the solution or look at the solution from Kodiak. Okay. Next thing is we'll do one more problem for relative velocity analysis, and then that's it. That will be the end of this lecture. Okay, so next problem. Determine the angular velocity of link AB and BC at the instant angle theta is 30 degrees. Also sketch the position of link BC when theta is 55 degrees, 45 degrees and 30 degrees to show its general plane motion. Don't worry about this part, we won't do it, so yeah, just cancel it. So we'll just calculate the angular velocity of link AB, that's this link, and BC, this link, okay, from the given data. So let's do it. So link AB is in pure rotation. Now when slider C, and slider C is in pure translation, and link BC is in both rotation and translation. So link BC is in general plane motion. So can you imagine the motion of link BC and AB when slider C moves up? Again, you can pause the video and think about it. So when C moves up, link BC goes has counterclockwise rotation, and link AB also has counterclockwise rotation. So this is omega BC and this is omega AB. We define our coordinate system. It's very important here. So this is X, this is Y, and we define that positive is right for X and positive is up for Y. So now there are two ways we can calculate the velocity of B. Now point B is interesting point because this is the point which is on link AB and it's also the point which is on link BC. So point B, there are two ways we can calculate the velocity of point B. So the first approach is we forget about everything on right of point B and just considered only link AB. So AB is in pure rotation, and using that information we can calculate the velocity of B with the cross product. So velocity of B with respect to A is omega AB cross RB relative to A, because A is the center of rotation. So this is one approach using that information that we have studied before. Okay. Second approach would be we block link AB and just think about that it's only link C and link BC, then what is the velocity of B relative to C if we know the velocity of C? So B has rotational motion counterclockwise relative to C. So velocity of B relative to C is omega BC cross RB relative to C. But that's not the final answer because C itself moves. So the absolute velocity of B is velocity of C plus velocity of B with respect to C. So remember that truck and Ferris wheel example. Okay. So consider C as a truck and this B as the cabin of the Ferris wheel. So that velocity of B is velocity of B relative to C plus velocity of C. And then we will equate both these equations and find out our unknowns. So those are two equations and we have two unknowns and we can solve for them. So we need two equations for two unknowns. So let's do the first part. Calculate the velocity of C from link AB only. So velocity of B is equal to omega AB. This is in vector cross RB relative to A. It's position of B relative to A. So let me put the arrow here. So it's this position, it's this vector which goes from A to B. So position of A relative to B. And you can see that this vector is going towards positive y. So it has only j component which is positive and no ith component. And omega AB has rotation in xy plane counterclockwise. So its magnitude is omega AB, but in its direction is positive k. Cross, this is 1 g because there is no ith component. So now when you multiply 1 with omega AB, it's just omega AB only, and then it's k cross j, and we know that k cross j is minus I. So this term is minus omega AB I. So let's call this our equation 1. Next is velocity of C. Absolute velocity of C is given as 6 feet per second. It's going up towards positive y. So its magnitude and direction is given by j because j is unit vector towards positive y. So let's call this our equation number 2. And the next part is at some point we need the velocity of B relative to C. So velocity of B relative to C is omega BC cross R B relative to C. And this vector is actually this line, okay, with the arrow at B. So RB relative to C. Now we know this value which is 30 degrees. So this angle is also 30 degrees. It's the same angle. Remember that this Z between two parallel lines, these angles are same. Okay. So if this angle is theta, then this angle is also theta. So now we will find out, we will just add, expand this term and we'll resolve the this into proper ing components. So let's work more onto this part. Okay. So VB relative to C once again is omega BC. So its magnitude is omega BC and its direction is positive k cross RB relative to C. So it's this vector, this tip of the point. My pencil is the arrow of the vector. And you can see that when you resolve this with using this 30-degree angle information, you will get negative I and positive j components. So it's minus 3 cosine 30 I plus 3 sine 30 j. and then we can actually, you can multiply 3 with cosine 30, that constant you multiply with omega bc, and then you can separate this cross product. So it's k cross I multiplied by this constant multiplied by omega bc plus k cross j, again that is multiplied with 3 sine 30 and omega bc. So when you do this yourself, you'll find that this is 2.59 omega bc, and this is j minus 1.5 omega bc I, and that's our equation third. So we can substitute, and then now we can write this equation for velocity of b, absolute velocity of b from c, that equation, that velocity of b is nothing but velocity of c because c is moving plus velocity of b relative to c. So that's here, and this is our fourth equation. So now it's time to substitute 1, 2 and 3 into the fourth equation. So let's do it. So we'll substitute value of VB from here. We'll substitute value of VC from here. I'll substitute value of B relative to C from equation 3. Okay, so let's substitute everything into that equation. So then it becomes minus omega AB I is equal to 6J minus 2.59 omega BC J minus 1.5 omega BC I. So this is our one big equation, which is actually equation 4 written using ij coordinates, ij components. And the next step is we need to separate I and j parts. So separate I and j, and we get two scalar equations, one from only I components and one from only j components. Okay, so from I only it's minus omega AV because that's with I. We don't have to consider 6 because it's with j. So the next one is minus 2.59 omega BC, and that's our equation 5. And we do that for j, so it's 0. Now it's 6 minus, oh sorry, I made a mistake here. So this is actually minus 1.5 omega BC. It's good to make mistakes, so it will give you the feeling of live classroom, right? So 0, then 6 minus 2.59 omega BC. And this is number 6. And next step, and then the last step is we have two equations and two unknowns, and two unknowns are omega AB and omega BC. So from equation 6 we can calculate omega BC and substitute that in equation 5 and calculate omega AB. And when you do that, you will get the answers as omega AB is 3.46 and the unit is radians per second counterclockwise, and omega BC is 2.31 radians per second, and this is also counterclockwise.